Hi everyone, in this video we are going to be talking about how to solve absolute value equations. You are going to learn in this video how to manipulate the absolute value symbol so that you can solve the equation both graphically and also algebraically, and that is going to entail a little bit of talk about interval notation and set builder notation since we're going to write our answers in those formats sometimes. All right, so let's start by just talking about what the absolute value means. In real world terms, the absolute value is the distance. It's going to be a very clear distance. It's the distance from 0 to some other number. So when we talk about absolute value, we're talking about the distance from a starting point, like 0, to some other number in relation to the 0. So let's talk about an example, and I think that will make more sense. Distance is our key here. The absolute value of x is equal to 4 is the same thing as saying the absolute value of x minus 0 is equal to 4. And when you think about the distance in this way, you read this as the answer, whatever x is the set of points whose distance starting at 0 is 4 units. So on a number line, if we start at 0 and we go 4 units, we could go 4 units in 2 different directions, to the left and also to the right. So let's count over 1, 2, 3, 4 to the right, and 1, 2, 3, 4 to the left. These two values for x are our solutions. So x is equal to -4 and x is equal to +4. In addition to thinking about this as a distance on a number line, we can also solve these problems by looking and thinking about them as functions. We want to ask ourselves this question: where are the two sides of the equation equal? In order to do that, we are going to graph both sides of the equation. So whatever's on the left-hand side, I'm going to graph that, and whatever's on the right-hand side, I'm going to graph that as well. So the absolute value of x, just to do a rough sketch, remember that is a vertex at 0, 0, and then it rises and runs 1. So it's going to go up at 2, 2, it's going to be at 3, 3, and 4, 4, and so on. On the other side, it's going to rise and run in the other direction, but in a symmetrical way. So then if I graph the second one, y is equal to 4, that's where y is always equal to 1, 2, 3, 4. So we're talking about this horizontal line where y is always 4 no matter what x is. So if we're looking at this system of equations, or two equations on the same coordinate plane, the solution is where they are equal to one another, which remember is what we were trying to find, when these things equal one another. So this intersection is when they're exactly the same, and this intersection is where they're exactly the same. So if I think about my rising and running that's happened, I am on the right at x is equal to 4, and on the left that's happening where x is -4. So my solutions are again -4 and +4. I also want to point out that you may see these answers written as a solution set, which is when in a set of squiggly brackets you have the numbers listed out that are the solutions, in this case -4 and +4. That is a legitimate way to write your answer, in addition to this equation that we've written as the answer for both of these. Let's look at another one of these. This next problem says that the absolute value of x minus 4 is equal to 3. So we can read that as a distance as the set of points whose distance from 4 is equal to 3, where again the number inside the h of the vertex is going to be where you start, and the 3 is the number of units that we're going to travel. So if I start at +4 and I go 3 units to the right, that puts me up here at 7, and if I go 3 units to the left, that puts me here at 1. So x is equal to 1, and 7 is my answer there. Now we can also solve this problem by thinking about the functions and where they're equal. We're going to graph the left-hand side, and we're going to graph the right-hand side. Now this left-hand side, the absolute value of x minus 4, that has moved to the right 2 units, or I'm sorry, 4 units. So let's go 1, 2, 3, 4, and that's our vertex, 4, 0. Now I'm going to use that rise and run of 1, because there's no a value out front, to get the right-hand side, which means I'm going to rise and run, rise and run, rise and run, and rise and run. And then my left-hand side is going to go symmetrically in the other direction, like that. Okay, so for the right-hand side now, let's graph y is equal to 3. That is going to be a horizontal line where y is 1, 2, 3. So that's going to be here, which means that my solutions are where these two graphs intersect. And that is happening at 1 and at 7. So again, my solutions are 1 and 7, no matter which way I do it, distance or as a function. And you can write your answer as a solution set of 1 and 7 as well. All right, let's do a couple of practice where we just think about either graphically or in terms of distance, what solutions work for these. If the absolute value of x is equal to 3, that's the distance from 0 is 3. So on a number line, the distance from 0 is 1, 2, 3, or to the left 3, which means our answers are plus and minus 3. Now this next one has a value, this stretch of 3 units. So I'm going to solve this one by graphing it, not by doing distance. So let's get a nice graph here. I'm going to have to start at 0, 0. That's my vertex because of my HK. And then I'm going to be rising and running quite a lot in this one. So I'm going to go all the way up to 12, and I'm going to go over maybe 5 both ways. All right, so if I'm going up 3, because my slope of the right-hand side is 3 over 1, that means I'm going 1, 2, 3, and over 1, then 1, 2, 3, and over another 1, 2, 3, and 1, 2, 3. So that's going to put me way up there. Okay, and then on the other side, I'm going up 3 each time again. So we have a nice stretched graph there. Then my right-hand side says that x is always equal to, or y is always equal to 12. So that's what that top one here was. And if I look down at where that's happening, it's happening at 4. And it's happening at negative 4. So x is equal to plus and minus 4 for this problem. All right, for this last one, 2x plus 3, or the absolute value of 2x plus 3 is 7. We can solve this one graphically. I also want to show you how to do this in the calculator. So let's pull the calculator over here. All right, so in your y equals, you put in the absolute value bars by hitting math, going to the right, choosing the first option. We're going to put 2x plus 3, and then in the y2, I'm going to put the right-hand side. I'm going to put the 7. So let's graph that and see what our picture looks like. It looks like it moved to the left a little more than 1. So we're going to move over to here for our vertex. And then it looks like, roughly sketching, it crosses up here somewhere. That's at y is equal to 7, the right-hand side. And we're looking for these values. In order to find them, you are going to go to second, trace, and then we're going to choose the intersection, 5. It's going to ask us for where the two curves are, or where the two lines are, the red one and the blue one. So the first curve, it's already on the blue one. There's my cursor there, so I'm going to hit enter. And then it's going to ask for the second curve, so my cursor needs to be on the red line now, which it is. That's why these numbers down here are red. So I'm going to hit enter again, and then I'm going to make my guess. So I'm going to do the right hand side first, so I'm going to move my cursor out that direction and hit enter, and it tells me that that's happening where x is equal to 2. Oops. And it's also happening over here, so I'm going to go to second trace again, work through my steps again. I'm going to choose the fifth option for intersection. I'm going to put it so it's only on the blue curve, hit enter. It's only on the red curve, hit enter. And then I'm going to move my cursor way over for that guess so that it's closer to that intersection and hit enter. And I can see that that happens where x is equal to -5. So my answers here are -5 and 2. All right, so now let's talk about checking your work for a moment. If you want to check your work, you can always substitute in your answers. To the original problem. That means that we can take, say, in this first practice problem that we did here, we can take this +3 and that -3 and plug it into the problem. When we plug in -3, what is the absolute value of -3? Well, it makes it positive, so that means it's +3. That checks. We also need to plug in the second answer, +3. When we plug that in, what is the absolute value of +3? It's 3. That checks with what the problem says, so that those answers are right. You can do the same thing with each of these. For the middle one, if I do the absolute value of 3 times -4, that is the absolute value of -12, which is equal to 12, so it checks. The absolute value of 3 times +4, which was my second answer, I have plus and minus 4, that gives me the absolute value of 12, which is equal to 12, so that answer checks as well. If you plug in these last two, they also should both equal 7 when you plug them in for the x. All right, so let's talk about solving algebraically now, because what we've been doing so far is graphical on a number line and also on a coordinate plane. So here come your steps for solving algebraically. Number 1 is to isolate the absolute value. If you look at this example, you can see that there is not just an absolute value on the left-hand side of the equation. There's also this -5. We need to move it over so it is only the absolute value and the stuff inside of the absolute value that's on our left. So I'm going to add 5 to both sides to do that. That leaves me with the absolute value of 3x plus 1 is equal to 2. Now I can do my step 2. I'm going to rewrite the equation as 2 equations, a positive version and a negative version. That's the whole distance piece where we're moving to the right a certain number of units and to the left a certain number of units. So I'm going to split this into 2. I'm going to look at the absolute value of 3x plus 1. I'm sorry, I don't need the absolute value. I'm just going to say 3x plus 1 is equal to 2. And then I'm also going to say the other option is 3x plus 1 is equal to -2. And that's where we're moving to the left on the number line. Either of these, one or the other, will be our solution. So let's solve now, which is step 3. We're going to solve both of these equations down. On the one that I have on the left, the positive case, we're going to subtract 1 first, and then we're going to divide by 3. So that gives me x is equal to 1/3. On the right-hand side, I'm going to subtract 1 first, and then I'm going to divide by 3. And that gives me that x is equal to -1. So I have 2 solution options here. I am not going to draw a box around either of these for my final answer yet. I need to check my solutions. And that is the 4th step. This is not an optional step. You must check your work because there might be solutions that I found here that don't actually work. Remember from a moment ago, we're going to check our work by plugging them back into the original equation. So in order to do our first check, we need to take this 1/3 and put it into the left-hand side. So we have the absolute value of 3, but instead of that x, I'm going to put in what I think x is equal to, 1/3. And then I'm going to finish writing out that left-hand side. Notice this is the left-hand side of this original equation, the entire thing, including the -5 outside of the absolute value. So now let's simplify. 3 times 1/3, those 3's cancel out, so that leaves me with just 1. 1 plus 1 is 2, and 2 minus 5 is -3. So that means that when I plugged in 1/3, I got -3 as my answer. And look, on the right-hand side, it says it ought to equal -3. So this one checks, and that is a solution to my equation. I can draw that final box around that now. Let's check the other one now. This time we're plugging in -1 to the original problem. So the absolute value of 3 times -1 plus 1 minus 5. That is going to give us the absolute value of -3 plus 1 minus 5 outside. And then that is the absolute value of -2 minus 5. The absolute value of -2 is 2, which gives us -3, and that checks because that was what the right-hand side told us our answer needed to be. So for this one, we have 2 solutions. If I wanted to write that in set notation, I would say that -1 and 1/3 are both solutions to this problem. All right, so let's do a couple of examples just to make sure we're all okay with this. This first one, we have nothing to isolate because it's just the absolute value bars on the left-hand side. So we're ready to rewrite it as 2 equations. Our 2 equations are going to be the positive and negative case. That means x plus 3 is equal to 8. And then it also might be x plus 3 is equal to -8, moving in the left direction. So let's solve these now. We subtract 3 from both sides, and that gives us 5. And then on the other one, when we subtract 3 from both sides, that gives us -11. So let's check your work now. For the first check, we need to plug in 5. So let's plug into the original problem. 5 plus 3, that absolute value is the absolute value of 8. And the absolute value of 8 is 8. So that checks. That's an answer. Let's do the right-hand one now. The absolute value of -11 plus 3, well, that is equal to -8. And the absolute value of -8 is +8, so that one checks. That's the solution. Our final solution set is -11, 5. Okay, let's try this next one now. This one, I have absolute value bars on the left-hand side with nothing on the outside, so that looks good. I'm ready to split this one. There's no isolating that needs to happen. The positive case is going to be 2x plus 12 is equal to 4x. The negative case, the other option, is 2x plus 12 is equal to -4x. So let's solve now. This time I'm going to subtract the 2x from both sides because that way I can combine my like terms. And then I'm going to divide by 2 on both sides. So that gives me that x is equal to 6. Let's do the negative case now. I'm going to subtract 2x again. That gives me 12 is equal to -6x, and then I'm going to divide by -6. That gives me x is equal to -2. So I have 2 possible options. Let's check your work to see if those both work. For the check, I'm first going to plug in this answer of +6 to the original problem. So the absolute value of 2 times 6 plus 12. That is the same as the absolute value of 12 plus 12, which is equal to 24. Now, if you look at the right-hand side, do you see how this has a 4x over there? I need to plug in my x, my 6, for this right-hand side too. 4 times 6, which was the x I'm checking for, that's equal to 24. And because these two things equal one another, That checks. So 6 is one of my answers. Let's check the other side now. Let's plug in our negative 2. The absolute value of 2 times negative 2 plus 12 is equal to the absolute value of negative 4 plus 12, which is equal to the absolute value of 8, which is equal to 8. Now, if I plug in my negative 2 on the right-hand side, because I have to do both, 4 times negative 2 is equal to negative 8. And since these are both, no, oh, hold it. What mistake did I make? Do you see it? Negative 4 plus 12 is 8. That should be positive. And 4 times negative 2, okay, so here we go, is negative 8. Positive 8 is not equal to negative 8, so this one does not work, and that is not a solution. All right, so let's try one more example now. This one's got some craziness, doesn't it? It has lots going on both sides. But notice that it's absolute value bars on the left and nothing else on the outside, so we can split this one. The positive case, it's going to be 4x plus 5 is equal to 2x plus 4. The negative case is going to be 4x plus 5 is equal to negative the whole thing, 2x plus 4. We'll solve that one in a second. Let's focus on this positive case first. I'm going to subtract 2x from both sides. I'm also going to subtract 5 from both sides. So that gives me 2x is equal to negative 1, which means that x is equal to negative 1/2. On the right-hand side, I need to distribute this negative first. So 4x plus 5 is equal to negative 2x minus 4, and then I can solve. So I'm going to add 2x to both sides. I'm going to subtract 5 from both sides. That gives me 6x is equal to negative 9, and then x is equal to negative 9 divided by 6, which simplifies because both are divisible by 3 to negative 3 over 2. Okay, so let's check your work. If we're going to plug in the negative 1/2 first, we have the absolute value of 4 times negative 1/2 plus 5. That is going to simplify so that we have the absolute value of negative 2 plus 5, which is equal to the absolute value of 3. And then when we plug the negative 1/2 in on the right-hand side, that's 2 times negative 1/2 plus 4, which is negative 1 plus 4. So that's 3. That checks because both of these gave me the answer of 3, which means that's part of my solution set. Let's check the negative case now. We're going to do the absolute value of 4 times my answer, negative 3 over 2, plus 5. So that is going to simplify. 2 times 3 is negative 6, so that's negative 6 plus 5, which means the absolute value of negative 1 is positive 1. And when I plug it in on the right-hand side, 2 times negative 3/2 plus 4, those 2's cancel out, and that leaves us with negative 3 plus 4, which is also positive 1. So because those are the same, this answer checks out too. My final solution is negative 3/2 and also negative 1/2. There's your solution set as well. Okay, so quick reminder, when you have an absolute value equation that has variables on both sides of the equal sign, like these second two that we've done, you need to always check for what's called extraneous solutions. Extraneous solutions are solutions that don't actually work. They don't check because they don't satisfy the original equation. They don't make a true statement. That happened in that second example that we looked at a moment ago here, where this one did not check out. A little bit of quick vocab. Extraneous solutions, like we just said, are solutions that look like they're answers. We get them when we solve algebraically, but we have to reject them because they don't check. They don't satisfy our original equation when we plug them back in. It is possible that you will get no solution to check as your answer. And the main reason that happens is because distance, which is what absolute value is, can never be negative. I can't go a negative distance. So if you see a problem like this, the absolute value of 2x plus 3 is equal to -7. You don't have to do the math for all of this. You don't need to isolate and rewrite the two cases and solve and check. As soon as you see that the absolute value is equal to just a negative number, you know that can't ever be true because you can't have an absolute value equal a negative. So you can write no solutions immediately. Now, I do want to point out, because a common mistake that students make is that if this problem had been 2x plus 3, the absolute value of 2x plus 3 is equal to -7x, this x means that I do have to solve the problem and check for extraneous solutions. Because if this x was, say, -4, -7 times -4 is 28, which means this absolute value problem is equal to a positive number. So it might work. This trick, this shortcut about absolute value never equaling a negative number is only when it's just a number. If there's a variable there, you're going to have to go through the steps and solve it algebraically. All right, so now you should be able to manipulate that absolute value so you can isolate it and solve the equation, either by looking at the graphs, either number line or the functions on a grid, or algebraically. And we've written your notation in set builder notation when we write those answers as a solution set. So go ahead and try that Now You Try problem now.